Okay, Energy Part 2, Lesson 2. So this lesson is all about energy efficiency. And we're going to be looking at how we can calculate the efficiency of any sort of device and understand ways in which dissipation of energy occurs. So we need to know what's meant by the word dissipation. So the first thing we have been asked to look at is we've been shown two light bulbs. We haven't been shown pictures of the light bulbs, but we've been given these two diagrams and we've been asked which light bulb is the most efficient and how can you tell. So obviously one of these diagrams is to do with one of the light bulbs, the other diagram is to do with the other light bulb. So which light bulb is the most efficient? Well, let's say this one is light bulb A and this one is light bulb B. Which one is most efficient? Well, I think we could say that the most efficient light bulb is B. Okay, right, so how can we tell that? Well, one thing we can look at is in terms of the numbers. So both light bulbs use 100 joules of electrical energy. But A only produces 10 joules of light energy, whereas B produces 75 joules of light energy. So they've both got the same amount of energy going in, but A only produces 10 joules of light energy, useful energy, and 90 joules of energy is heat. Whereas in B, 100 joules of energy going in gives us 75 joules of light energy coming out and only 25 joules of heat energy. The other way we can tell is with these diagrams, you won't be asked to draw one of these diagrams, but they're known as Sankey diagrams, and they're really useful because the arrow that goes down is the wasted energy, and the arrow that comes out at the top, that's the useful energy. So we can see in this case we've got a very thin useful energy arrow and a very wide wasted energy arrow, and the opposite is true for light bulb B. So the width of the arrow tells us how much of the energy is useful, how much of the energy is wasted. So we've got very little useful energy, lots of wasted energy. Lots of useful energy here, very little wasted energy. So this one we can say is more efficient. Okay, right, now the next question asks, state the law of conservation of energy. So this is just to remind us of something we met before, but it's very important that we always bear this in mind. So energy can be stored, transferred, or dissipated. There's that word again, dissipation, which we'll learn about later. But it cannot be created or destroyed. So it's really important when you're talking about energy that you never use either of these words, created or destroyed. This is quite a thing to think about, because what this is saying to us is that the amount of energy that existed in the whole universe at the time of the Big Bang, so 1 second after the Big Bang, the total amount of energy that there was in the universe is exactly the same as the total amount of energy there is now. No extra energy has been created since the Big Bang, and none of the energy has been destroyed. It's only changed from one form to another or stored in an object. Right, then we have a closed energy system. In a closed energy system, that is one where in which there is no change to the total energy in the system. So we have already said that energy cannot be created or destroyed. But if we think about a system, now that is an object or a group of objects, and although energy can't be created or destroyed, it can be transferred away from the object. And in particular, if there is wasted energy, so like we had heat energy being produced by our light bulbs, that heat energy doesn't stay with the light bulb, it doesn't stay in the system. It goes away into the atmosphere, it heats up the air around the light bulb, and gradually that heat energy disappears into the atmosphere. It's not destroyed, but it's just been spread out into the atmosphere, and we say that it's dissipated. If we have a closed system, it means there's no change to the total energy in the system. So no energy is dissipated. Energy might be wasted, but it doesn't escape away from the object or the group of objects. So what would be an example of an open system? An open system would be something like water being heated in a saucepan with no lid. So here, energy, the hot water inside the saucepan, where there would be steam coming out of the surface of the water going into the air surrounding the saucepan. And also the saucepan itself would be becoming hot, and that heat energy would be heating up the air around the saucepan, and hence some of the energy is being dissipated. So this is an example of an open system. A closed system would be something like a thermos flask. So in a thermos flask with a lid, so here no energy is getting in or out, and there is no matter getting in or out. There's no steam coming off this, and there's no heat energy being dissipated. So no energy going in or out, and no matter going in or out. So that would be a closed system. Okay, so we're going to look at dissipation in a little bit more detail, and this is really looking at the example once again where we have something like our light bulb A, and a certain amount of energy goes in, and pretty much most of that energy is wasted, and I've got a little bit of useful energy up at the top. So that's my useful energy, this is my wasted energy, and this is the energy I've put in. Okay, right, so let's see how this works. We say in all systems, some of the energy is transferred to a useful energy store. For example, the light from our light bulb. But the rest of the energy is transferred to a wasted energy store. Okay, so in the case of this example, where we had thermal energy here, heat energy as our wasted energy. So the thermal energy, and we could say heat. So thermal energy is not useful in this case, and can be considered to be dissipated or wasted energy. Now, dissipated means that the energy moves away from the system. In most of the cases that we would deal with, that means it moves into the atmosphere. Eventually, all the energy becomes dissipated to the surroundings as thermal energy. Okay, so what's the difference between the filament bulb and the energy saving bulb? Well, looking back here, this is our filament, the old style light bulb. This is the energy saving bulb. So we can say, what is the difference between these two? Well, more of the energy, input energy, is becoming dissipated or wasted energy here, whereas here more of the energy, input energy, is becoming useful energy. So in the energy saving bulb, more of the input energy is being transferred to useful energy store, whereas in the filament bulb, more energy is dissipated. So you probably won't have come across one of these old style filament bulbs. One of the problems with them that certainly your parents might remember is that if you did have to change one, you would have to wait until it cooled down. They would become very, very hot because so much energy was being dissipated as heat energy. So we've talked about this idea of this one is more efficient than this one because it's got more useful energy out than this one. So we can talk about this in terms of something called efficiency. And efficiency is a measure of how good something is at converting energy from one form into a useful form. And this is the most important thing to remember. We're talking about how much of the input energy is transferred into a useful form or a useful energy store. We write it as a percentage or a decimal, and it can be calculated from either power or energy using the following equations. Now, these equations, uniquely in the GCSE physics, there are no symbols for these equations. So it's always written as words. So efficiency is equal to, we have the useful output energy divided by the total input energy, or we can say that the efficiency is equal to the useful power out divided by the total power in. Now, if we look at these diagrams, remember we're saying efficiency is how much useful energy has come out divided by how much energy has gone in. Clearly, this arrow, because how much has gone in is shared between these two arrows, this number is always smaller than this number. So this number, it is always less than 1, or always less than 100%. And if we do want to write this as percentage rather than a decimal, once we've done this calculation, we multiply by 100 if we want to write it as a decimal. Right, so we asked to do a little bit of rearranging again. So we said rearrange the equation for efficiency to get the equation for useful power output. So remember, we have efficiency is equal to useful power out divided by total power in. So we want to get rid of the divide by total power in part, which means that useful power out is equal to the efficiency multiplied by the total power input. And then rearrange the equation for efficiency to get the equation for total power input. Well, in this case, we've got efficiency equals total power output divided by total power input. That gave us this rearrangement. So we want to get rid of the efficiency in this case, so we need to divide both sides by efficiency. That gives us total power input is equal to useful power output divided by efficiency. But the thing to remember always in these calculations is whatever number you work out for efficiency, it must be less than 1. And obviously if you multiply that by 100 to make a percentage, the answer must be less than 100%. Okay, so we have some calculation questions to do, and we're going to start by looking at this question, and we have to make sure we're showing all our steps. It does tell us that they want us to give the answer a percentage, so we have to remember that we're going to be using this form of the equation with the multiply by 100 at the end. Okay, so what are we told? We're told that it's got 500 joules of electrical energy to do 200 joules of cake mixing. So the total energy in is equal to 500 joules. And the useful energy out is equal to 200 joules. How do I know that? Well, it's a food processor, and we've asked it to do cake mixing, so this is the useful energy out, the energy used in the cake mixing. So this is 200 joules of useful energy out for 500 joules total energy in. Now the equation is the efficiency is equal to the useful energy out divided by total energy in. And they want the answer as percentage, so I need to multiply by 100 to get it as a percentage. So now I can put in the numbers to replace my words here from what I've written from part 1. Useful energy out is 200 joules. Total energy in is 500 joules. Multiplied by 100. So the efficiency, and don't forget, we always use our calculator to be sure that we get the right answer. So we've got 200 divided by 500 to give us an answer of 0.4 multiplied by 100, so that gives us an answer of 40%. Okay, now I'm happy with that answer. Can't be 100% sure it's right, but it is less than 100%. So that's what we would expect, an answer less than 100%. Okay, so we've got a number of other questions to answer. So we're going to work our way through these. I'm just going to stop the video here and I'll work through the answers. So when the answers appear on the screen, if you want, you can pause the video so you can check all your answers. Okay, so here are these 5 questions answered. And you can just pause the video to check each of your answers to make sure you got it right. And you'll notice that some of the calculations have been done as decimals and some have been done as percentages, particularly if it asks for percentages efficiency, which it did here. I'll just fix that last part. One thing to notice here is with this question, which has an answer of 8.3, the answer is actually 8.3 recurring. We never in physics write recurring like that, and you would never write it like this. You always round it, so in this case to 8.3%. So that the last one calculated as percentage efficiency, so I've written it as decimal, so I'd have lost a mark there. I need to write that as 25% because I wrote it as a decimal. Okay, so you can just pause the video and check your answers. Now with this question, this is more typically how questions are presented in exams, with a little bit of the information presented in a slightly different form. So instead of having, again, the information in the form of numbers put in a sentence, in this case all the information has been put into a table. So we need to use the table to get information we need to do our calculations. But the steps are always the same. So part A says calculate the efficiency of each bulb. So I'm going to start we've got an energy efficient, a standard and fluorescent strip. So I've got 3 bulbs and I have to write the answers in the table. So I'm just going to make 3 parts on my page here. So this is going to be the energy efficient bulb, this is the standard bulb, and this is the fluorescent strip bulb. But I always use the same steps. So step 1, I'm told the power rating. Now the power rating means the power that's input. So the power in is equal to 20 watts. And I'm told that the power wasted is equal to 1 watt. In this case, for the standard one, the power in is 100 watts and 80 watts is wasted. And for the final one, I'm told the power in is 20 watts and 8 watts is wasted or dissipated. Okay, what can I do now? Well, the first thing I can do is I can say, well, that means that the power that's useful is going to be equal to the power that I put in, take away the power that's wasted. Because remember, what's happening in here is my energy or power coming in, and it's shared between the useful energy and the wasted energy. So the useful energy is equal to how much was put in, take away how much is wasted. So here I've got 20 watts minus 1 watt, that leaves me with 19 watts of useful energy out. For this one, I have 100 minus 80, so I've got 20 watts of useful energy out. And for this final one, I've got 20 watts in and 8 watts out, so that's going to leave me with 12 watts of useful energy. Okay, so now I'm asked to calculate the efficiency. So the efficiency is equal to the useful power out divided by the power in. Okay, and I have to write it as a percentage, so I need to multiply each of these by 100%. Okay, so now I can substitute in my numbers. So I've got for this one, the efficiency is equal to 19 watts divided by 20 watts in times 100. This one, the efficiency is equal to 20 watts out divided by 100 watts in times 100. And this last one is equal to, I've got 12 watts out divided by 20 watts in times 100. So now, once again, using my calculator, I can work out my answer. So for this one, the efficiency is equal to 19 divided by 20, very large number, and multiply by 100, which gives me 95%. Okay. Then for this one, I've only got 20 watts divided by 100, so that gives me a small number, 0.2, times 100. So the efficiency of this one is 20. And then the final one, I've got 12 divided by 20, so that's somewhere in between. The efficiency is 60. And it asks us to write the answers in the table, so that gives me 95%, 20%, and 60%. So not the simplest question, because we needed to realize that we had to calculate the useful power by taking away the wasted power from the input power. And there's quite a lot of calculations to do, but we can see that it's exactly the same steps, just repeated for each light bulb. Okay, so which type of light bulb is the least efficient? Well, now that's easy to see. That's straight from the table. It's 20% efficient, the others are 95 and 60, so it's the standard one. Where does the wasted energy go? It's dissipated as thermal energy, and it's always a good idea to say into the surroundings. So the light bulb heats up and heats up the air around the light bulb. Give 2 reasons why energy efficient bulbs are considered to be better for the environment than standard bulbs. Okay, so this last part, one part of this answer just comes straight out of the table. The other part is something that you would just need to know. So the first part we can say is, well, why are energy efficient better for the environment than standard? Well, we can see that it uses less input power. So we can say it uses less input power, hence less electricity, so less fossil fuels need to be burned. So that's where electricity is generated using something like a gas-fired power station. And we could add for the same light output. Because what you'll notice is that the standard lamp, although it's putting 100 watts in, it was producing 20 watts of useful light energy. This one is pretty much the same at 19 watts, very, very similar amount of light energy produced out. The other reason why these are useful is they last longer than a standard bulb. So that's just something you would need to know. Okay, so last part of this lesson is a facts quiz. Now, it's really important that you review and recall as many things as you can, as often as you can. It's going to make it very much easier for you to recall things when you come into exam. So, what is the unit of gravitational field strength? That is newtons per kilogram. On a velocity time graph, a horizontal line represent constant speed. This is very easy to get wrong. People often say stationary, but that's on a distance time graph. A velocity time graph, horizontal line is constant speed. What's typical reaction time? Typical reaction time around about 0.2 to 0.9 seconds, something around that. On a distant time graph, a straight line represents constant speed. So this seems the same what this is saying. Here's my velocity time graph. This is in seconds. That's constant speed in a velocity time graph. When I've got distance time graph, that's constant speed on a distance time graph. What is the unit of the spring extension? Well, that's simple, that's meters. Now, what are the units of energy? So now we're into more to do with our topic that we're exploring. What are the units of energy? The units of energy are joules. What is the energy transferred by electromagnetic radiation? That's radiation transfer. What is the equation for calculating efficiency from power? So efficiency is equal to useful power out divided by total power in. We start to see with these efficiency equations how useful it is to use symbols rather than having to continuously write out all the words. What is magnetic energy store? That is the energy stored in a magnet in magnets, repelling or attracting. And what is the energy transferred when a charge moves? So when a charge moves, that's in an electrical circuit. So this is in this here, they're talking about an electrical circuit. So how has the energy been transferred? It's been transferred through electrical transfer.